Introduction to TCP Zero Window. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. In this presentation, we are going to explore one of the most common yet often misunderstood TCP performance issues: the TCP Zero Window condition. Understanding this concept is essential for anyone who troubleshoots network performance problems, whether you are a network engineer, systems administrator, or DevOps professional. TCP Zero Window is a flow control mechanism that occurs when a receiver tells the sender to stop transmitting data because its receive buffer is completely full. This is not an error condition but rather a protective mechanism that prevents the receiver from being overwhelmed with more data than it can process. When this happens, the receiver advertises a window size of 0 bytes in its TCP header, signaling to the sender that it must pause transmission until buffer space becomes available. The reason this matters is that TCP Zero Window events directly impact application performance. When a receiver cannot keep up with incoming data, the sender must wait, causing delays in data transfer. In high-performance environments, frequent zero-window conditions can indicate serious bottlenecks in the receiving application, insufficient system resources, or misconfigured buffer sizes. Let me walk you through the diagram that illustrates the TCP window advertisement process. The diagram shows 3 participants in this communication flow. First, we have the sender, which represents the TCP endpoint that is transmitting data. The sender maintains a send buffer where outgoing data is queued before transmission. Next, we have the network, which represents the communication path between the 2 endpoints where TCP segments travel. Finally, we have the receiver, which represents the TCP endpoint receiving the data and processing it through its receive buffer. The sequence begins when the sender transmits data to the receiver through the network. The data flows from the sender, passes through the network, and arrives at the receiver. Upon receiving this data, the receiver examines its receive buffer capacity and determines how much additional data it can accept. The receiver then sends an acknowledgement back to the sender through the network. This acknowledgement includes a critical piece of information: the window size, which tells the sender exactly how many bytes of additional data the receiver can accept at this moment. Based on this window advertisement, the sender adjusts its transmission behavior. If the window size is healthy, the sender continues transmitting. If the window size is 0, the sender must stop transmitting and wait for the receiver to advertise a non-zero window. This constant exchange of window advertisements is how TCP implements flow control to ensure reliable data delivery without overwhelming the receiver. Causes of TCP Zero Window. TCP Zero Window conditions can arise from various sources, and identifying the root cause is crucial for effective troubleshooting. The causes generally fall into categories related to the receiving application, system resources, or network configuration issues. Let me walk you through the most common scenarios that lead to zero window events. Application processing delays are the most frequent cause of TCP Zero Window. When the receiving application cannot read data from the socket buffer quickly enough, the buffer accumulates data until it reaches capacity. This situation often occurs when the application is performing intensive computations, waiting for disk I/O, or blocked on database queries. The application becomes the bottleneck, and the TCP stack has no choice but to signal the sender to stop. Insufficient system resources present another common cause. If the server has limited CPU capacity, the application may not receive enough processing time to handle incoming data efficiently. Memory constraints can also play a role, particularly if the system is under memory pressure and the kernel reduces buffer allocations. In virtualized environments, resource contention with other virtual machines can create similar effects. Small socket buffer configurations can trigger zero window conditions even when the application is processing data reasonably well. If the default receive buffer size is too small for the application's workload, the buffer fills quickly during traffic bursts. This is particularly common in high bandwidth, high latency environments where larger buffers are needed to maintain throughput. The diagram presents a decision tree that helps identify zero window causes. The process begins at the zero window detected node, which represents the starting point when you observe zero window events in your traffic analysis. From this starting point, the first question to ask is whether the CPU utilization is high on the receiving system. If CPU utilization is high, indicated by the yes path from the high CPU question, the flow leads to the CPU bottleneck node. This diagnosis means the application cannot process data fast enough because the processor is overloaded. The recommended actions in this case include optimizing application code, adding CPU resources, or distributing the load across multiple processors or servers. If CPU utilization is not high, indicated by the no path, the next question examines whether the application is blocked waiting for resources. This could mean the application is waiting for disk I/O, database responses, or logs. If the application is blocked, the flow leads to the application blocked node, indicating that the receiving application has stopped reading from the socket while waiting for some other operation to complete. The solution involves identifying and resolving the blocking operation. If the application is not blocked, the final consideration is whether the socket buffer size is adequate for the workload. Following this path leads to the small buffers node, which indicates that the receive buffer configuration is insufficient. The solution involves tuning the socket buffer sizes at the system or application level to accommodate the traffic patterns. This diagnostic flow represents the systematic approach you should take when investigating zero window events, starting with the most common causes and working through the possibilities methodically. Introduction to tshark for TCP analysis. Now that we understand TCP Zero Window conceptually, let us introduce tshark, the command line tool we will use for analysis. Tshark is the terminal-based version of Wireshark, providing the same powerful protocol analysis capabilities in a scriptable, automation-friendly format. For TCP troubleshooting, tshark offers significant advantages over graphical tools when working with large capture files or remote systems. Tshark can capture live traffic from network interfaces or read previously captured files in PCAP or PCAP-NG format. Its display filter system allows precise identification of specific TCP conditions, including zero window events. The ability to output in various formats makes tshark ideal for integration with other analysis tools and scripts. The command line nature of tshark makes it particularly valuable for server environments where graphical interfaces are unavailable. You can run tshark directly on production servers to capture traffic, then transfer the capture files for detailed analysis, or perform filtering operations remotely to extract relevant packets. Let me explain the code block that shows basic tshark commands for TCP analysis. The first command demonstrates how to capture traffic and save it to a file for later analysis. The command begins with tshark, which invokes the tshark program. The -i eth0 option specifies the network interface to capture from. The -i flag stands for interface, and eth0 is a common name for the first Ethernet interface on Linux systems. You would replace eth0 with your actual interface name, which you can discover using commands like iplink or ifconfig. The -w capture.pcap option tells tshark to write the captured packets to a file named capture.pcap. The -w flag indicates write mode, and pcap is the standard packet capture file format. This creates a binary file containing the complete packet data for later analysis. The second command shows how to read a capture file and apply a display filter. The command starts with tshark followed by -r capture.pcap. The -r flag indicates read mode, telling tshark to read packets from the specified file rather than capturing live traffic. The TCP option applies a display filter to show only TCP packets. The Y flag specifies a display filter using Wireshark's filter syntax. In this case, the simple filter TCP matches all TCP traffic. Display filters are powerful and can be combined to create complex selection criteria. The third command demonstrates how to list available network interfaces. The command tshark -d uses the D flag to enumerate all capture interfaces on the system. This is useful when you need to identify the correct interface name for capturing traffic on a system you are not familiar with. The fourth command shows how to filter for a specific TCP port. The -y TCP.port equal operator 443 inches filter matches TCP traffic where either the source or destination port is 443, which is the standard port for HTTPS traffic. The double equal sign is the equality operator in display filter syntax. These basic commands form the foundation for more advanced TCP Zero Window analysis that we will explore in subsequent slides. Advanced tshark filtering techniques. Beyond basic zero-window detection, tshark provides sophisticated filtering capabilities that allow you to analyze specific aspects of TCP flow control problems. Advanced filters help you correlate zero-window events with other TCP conditions and extract detailed statistics about problematic connections. The TCP.window_size_value field gives you the raw window value from the TCP header, allowing you to track how the window changes over time. By filtering for small window values, you can identify connections that are approaching zero window conditions before they actually occur. Combining zero window filters with connection tracking filters allows you to isolate specific TCP streams for detailed analysis. The TCP.stream field assigns a unique number to each TCP connection, making it easy to follow a single conversation through a capture containing many connections. Let me explain each command in the code block for advanced filtering. The first command extracts specific fields from zero-window packets in a structured format. The command begins with tshark -rcapture.pcap to read from the capture file. The y tcp.analysis.0_window filter selects only zero-window packets. The T fields option changes the output format to display specific fields rather than the default packet summary. When using T fields, you must specify which fields to extract. The eframe.time option extracts the packet timestamp. Each E option adds another field to the output. The EIP.source extracts the source IP address. The EIP.destination extracts the destination IP address. The ETCP.source port extracts the source TCP port number. The ETCP.destination port extracts the destination TCP port number. The resulting output shows these 5 fields for each zero-window packet, separated by tabs by default. The second command tracks a specific TCP stream identified by its stream number. The filter TCP.stream equal operator 5 isolates all packets belonging to TCP stream number 5. Stream numbers are assigned sequentially starting from 0 as tshark encounters new connections. Once you identify a problematic stream, this filter lets you examine its complete history. The third command identifies connections with small window values that may be approaching zero window. The filter TCP.windowSize value less than 1000 and not TCP.analysis.0window finds packets where the window is small but not yet zero. This helps you identify connections under pressure before they completely stall. The fourth command generates summary statistics for the capture. The zconv, TCP option produces a conversation statistics table showing all TCP connections in the capture. This includes byte counts, packet counts, and duration for each connection, helping you identify which connections transferred the most data or experienced the most issues. The fifth command combines zero-window detection with expert analysis information. The z-expert option generates a summary of all expert information events detected in the capture, categorized by severity. This provides an overview of all TCP issues, not just zero window, giving you context for the overall health of the captured traffic. Troubleshooting workflow. Effective troubleshooting of TCP Zero Window requires a systematic approach that combines packet analysis with system-level investigation. The goal is to identify not just that zero window is occurring, but why it is occurring and what changes will resolve it. The troubleshooting process begins with quantifying the problem. Before making any changes, establish baseline measurements of zero window frequency, duration, and affected connections. This data helps you confirm that your remediation efforts are actually improving the situation. Correlating packet analysis with application and system metrics is essential. While tshark tells you what is happening at the network level, you need operating system tools to understand what the application and kernel are doing. Combining these perspectives reveals the full picture. Let me explain the comprehensive troubleshooting commands in the code block. The first command establishes a count of zero window events as a baseline measurement. The command tshark -- or capture.pcap reads the capture file. The -y tcp.analysis.0_window filter selects zero window packets. Piping to wc-l counts the number of matching packets. Running this command before and after making changes tells you whether the changes had a positive effect. The second command examines TCP socket buffer configurations on a Linux system. The command cat/proc/sys/net/ipv4/tcp_rmem reads the kernel parameter that controls TCP receive buffer sizes. This file contains three values: minimum, default, and maximum buffer sizes in bytes. If these values are too small for your workload, increasing them can prevent zero window conditions. The third command monitors socket buffer usage in real time. The command ss---tnp runs the ss utility, which displays socket statistics. The -t flag shows TCP sockets only. The -n flag displays numeric addresses instead of resolving host names. The -p flag shows the process using each socket. This output includes receive queue sizes, helping you identify connections with full buffers. The fourth command increases the TCP receive buffer maximum. The command sudo sysctl-wnet.ipv4.tcp_rmem equal operator 4096-131072-16,777,216 inches modifies the kernel parameter. The sudo prefix runs the command with administrator privileges, which is required for changing kernel parameters. The sysctl-w option writes a new value to the specified parameter. The three numbers set minimum buffer to 4096 bytes, default to 131072 bytes, and maximum to 16,777,216 bytes. Increasing these values allows the kernel to allocate larger receive buffers when needed. The fifth command identifies the specific streams experiencing zero window events. The etcp.stream field extraction combined with sorting and counting using sort and unique C produces a list of stream numbers with their zero window counts. The streams with the highest counts are your primary targets for investigation. Resolution strategies. After identifying the root cause of TCP Zero Window events, you can apply targeted resolution strategies. The appropriate solution depends on whether the issue stems from application behavior, system configuration, or resource constraints. Application-level improvements often provide the most significant and lasting resolution. If the application's processing logic is inefficient, optimizing the code reduces the time data sits in the receive buffer. Implementing asynchronous processing patterns allows the application to read from sockets more frequently, preventing buffer accumulation. System tuning addresses configuration-related causes. Increasing socket buffer sizes gives the application more headroom to handle traffic bursts. Tuning kernel parameters related to memory allocation and TCP behavior can improve overall performance. However, tuning without understanding the root cause may simply mask the problem temporarily. Infrastructure scaling becomes necessary when the workload exceeds what a single system can handle efficiently. adding more processing capacity through additional CPUs, migrating to faster hardware, or distributing the load across multiple servers may be required for high-volume applications. The diagram summarizes the resolution strategy decision tree. The process begins at the root cause identified node, which represents the conclusion of your diagnostic investigation. From this point, 3 primary resolution paths branch out based on what you discovered. The first path addresses slow application causes. When the application itself is the bottleneck, the flow leads to several possible actions. Optimized code represents improving the application's data processing efficiency. Async processing involves restructuring the application to handle network I/O asynchronously, preventing blocking operations from stalling socket reads. These application-level changes often provide the most effective long-term resolution. The second path addresses small buffers causes. When buffer configuration is insufficient, the resolution involves increased buffer size at the kernel or application level. Additionally, tune TCP_RMEM specifically adjusts the TCP receive buffer kernel parameters we discussed earlier. These configuration changes can provide immediate relief while longer-term solutions are developed. The third path addresses resource exhaustion causes. When the system lacks sufficient resources, the solutions involve scale infrastructure options. Add CPU cores provides more processing capacity. Add memory allows larger buffer allocations. Load balance distributes the workload across multiple systems, reducing the burden on any single server. Each resolution path may require iteration and verification. After implementing changes, return to your tshark analysis to confirm that zero window events have decreased. Continue monitoring over time to ensure the solution remains effective as workload patterns evolve. Thank you for your attendance. Please consider subscribing to the channel and liking this video.